Okay, so we stopped at the stream cipher last time on Monday. Now we're going to talk about block cipher modes of operation. This topic is pretty easy to forget because there are many similar things, and then everything looks very similar, and the topic isn't too interesting either. That's the problem. But anyway, fortunately, it is not too important. It's not not a vital. It's not a vital concept. It's a little bit boring, but I can't skip this. So anyway, I would try my best to make it as interesting as possible. So modes of operation, it's the way to use that. How to introduce this, how to bring out this concept. We can think of it this way. We only have a block cipher or string cipher. And how do you use this? Let's say we have a DES. It only works on 64-bit blocks. Well, when you have data, some actual data, is it going to be exactly 64 bits? Number one, okay. Most likely you will have something that's a lot bigger. Let's say you have a book or a PDF file to encrypt. Well, it will be like 700 K, less than one mega. If you have a video clip, that'll be most likely like 5 megabytes, something like that. How do you use this? You only use we only have a tool that allows us to encrypt 64-bit data, right? Apparently, you have multiple 64-bit blocks. Then how to apply those? Let's talk about the most naive way. The most naive way is this. We simply chop our data into 64-bit pieces, and then we use the same key. In every block, you have to use the same key, right? So for every block, let's say we have n blocks, C1, C2, until Cn. So for every block, we use the same key, K. Do you think this is good? Well, if your data is not too big, and if your encryption algorithm is reasonably secure, so if you have a few blocks, let's say 20, 30 blocks, that should be fine. Okay, this is called the ECB mode, electric code book. Now, very straightforward. Advantages. It's easy. Okay, easy. Disadvantages. The weakness. We have some weakness because we reuse the same key. But this is a block cipher. It's not a stream cipher. So it's not that we cannot use the key over and over again. It's not an absolute rule because block ciphers are designed to be a little more secure. Okay? So we can reuse the key, but not too much. For example, you have like 1 gigabyte. Then that's too much because you will be giving your attacker too many samples of encrypted and plaintext pair, right? That's too many samples. So in that case, that's not good enough. But if you have few KBs, okay, few kbytes of data, then it's fine. So if you have a little bigger, if your file size is a little bigger, then we use the second one. This is called the CBC mode. This is called cyber blockchaining. Let's take a look at this. So we have this is our plaintext, P1, P2, until Pn. We add some extra step in order to make it more secure. The first thing is we use another block called the IV, initial vector. So this initial vector should be as large as your plaintext block. Okay, that's the size of your block cipher. In the case of DES, but 64 bits. First we do the XOR, okay? And then this IV is actually regarded as part of the secret. So both your IV and UK should be kept secretly. So IV is going to be XORed with P1 first, and then we apply the encryption algorithm. Okay? Then after that, you take the ciphertext of the first block, and then simply you take it to the second block, and then it does exactly the same thing as IV does in the previous round. So this is going to be XOR with P2, and so on and so forth. Okay. So in this case, even though you reuse the same key, it makes the attacker much harder to attack. The reason is because of this XOR, that makes each block dependent on the previous one. So even though you have exactly the same plaintext, that could well be, but because of this XOR, you're going to end up with different ciphertext. So there's no way to block the attacker is able to know that the relationship between plaintext and ciphertext. It makes it much harder to attack. This is called the CBC mode. Okay? And the decryption is just the opposite. No big deal. You take the C1, okay, you recalculate, and then you do the XOR. This is called cyber block chaining. Okay, let's take a look. So each ciphertext block depends on all messages block that appears before that. Okay, so later blocks depends on previous blocks. And it needs initial values, or sometimes called initial vector, IV. Okay, and should be kept as part of the secret. And this is also part of our ISO standard as well. Now, let's take a look at the third one. It's called cipher feedback. Now, let's take a look. What's interesting is that, let's take a look. Okay, this is the third one. It's a different way of using the cipher, and achieves roughly the same result as a CBC mode. We have an initial value as well, or initial vector, and then we perform some circular shift. This is no big deal. And then we do the encryption. But what's interesting is that we're not actually encrypting our plaintext. We actually encrypting the initial value, right? It's a different way of manipulation. After that, we do some circular shift, which is no big deal again. The actual encryption comes after this. And the actual encryption is just XOR. So you encrypt the initial value and then XOR with the plaintext instead of encrypting the plaintext. So it's a different way of manipulation. From a security point of view, seems to be okay, and it's no big difference. The difference is not significant. And then we do this again. Yeah, we take the ciphertext. The ciphertext of the previous block plays the role of the IV in the first block. So just keep going. This is called cipher feedback. Okay. Now, I'm going to show you another one, which looks like the CFV mode. You guys pay attention and then tell me what the difference is. So this is CFV. Just look at the diagram because the descriptions is difficult to understand. Yeah, I think it's much easier to understand the diagram. Okay, I'm going to show you the next one. Okay, CFV. What's the difference? This is called OFB. The difference is subtle. Can you guys figure out any difference between the OFB? I'm gonna switch back again. I'm gonna go back and then let you guys compare. Okay. So look at this for 10 seconds and I'll go back. This is OFB. Okay. This is CFB. So what's the difference?
They take different parts.
Yeah. Yeah, yeah. So the difference is subtle, right? The difference is really subtle. Instead of taking the ciphertext, it actually takes this, the thing that gets XORed with, that's going to get XORed with P1. Take this to the next block. Well, actually, the difference is subtle, but it's significant. It makes these two modes fundamentally different. We can even say that this mode is more different from the CFB than it is from the CBC. But this is more different. So it's just that subtle difference. It's really significant. The main significance is that you actually don't need plain text to do this calculation. You don't need the plain text, right? Let's say you don't have this P. Can you do these calculations? No problem. So this calculation can be done before your plain text comes in. Let's go back and look at the previous one, the CFB. Can you do this? Can you do such type of pre-computation in the CFB mode without the knowledge of the plain text? No. You have to have your plain text in order to do this calculation. Right? How about the CBC, cipher blockchain? Can you do that? This is CBC mode. Without the knowledge of the plain text, can you do any calculation at all? The CBC mode. Without P1, P2, can you do any calculation? No. Yeah. That is why I said the OFB mode is more different from any other. This is like really, really different. So such difference is enough to enable us to do pre-computation. And this actually acts like, if you do pre-computation, you calculate everything before the plain text comes in. It's almost like the pseudo-random number generation. Right? You're actually calculating these pseudo-random numbers, and the actual encryption is nothing more than XORing the pseudo-random number with your plain text. That is why it's a fundamentally different mode. It almost turns a block cipher into a stream cipher. So sometimes we call this the stream mode. The stream mode. Yeah, that's the OFB. And then all those modes. So we have CBC and CFB, and these are kind of like traditional mode. And then we have the OFB mode, which is a little different, stream mode. And then those are not enough, because sometimes if you need to encrypt large data, you need other mode to do parallel computation. So all previous modes, you cannot do parallel computation. Even the stream mode, you can do pre-computation, but these calculations in each block cannot be done in parallel. So you still have to have the first block, the first IV. You still have to have the IV, and then do sequential computation. But sometimes, especially these days, we really prefer parallel computation. Sometimes you have like 16 core CPU. To calculate those, 16 core CPU won't make any difference because you still have to do serial computation, right? These things cannot be divided and calculated independently because one depends on the other. The latter depends on the previous one. So that is why we in order to facilitate parallel computation, we need newer modes. So this is called CTR mode. For counter mode, for each block, there's a counter. Okay, we don't use the initial value. We use the counter. The counter, and this is the counter plus one, and so on and so forth. If the size is not too small, then it works. Even if it's a little bigger than ECB, it's still much better than ECB sizes. For example, like a few kbytes, that's fine. So it's very efficient because we can do parallel encryption. Okay, and we can also do pre-calculations as well. Anyway, these modes are both the CTR mode and the ECB, electronic code book. They're limited to use with smaller plain text. Now let's take a look at the real mode. This is the mode used in the transcend USB flash drive. It's called XTS mode. So the mode are like that. Okay, it's a new mode. So less than 20 years ago, that's really new, right? 20 years ago, anything designed 20 years ago is new. Okay? Anything designed 10 years ago is designed yesterday. Okay? So this is mode. This mode is new. Okay? The tweaked block cipher, and this mode is actually used in lots of USB flash drives. That is why I think it is worth introducing. And it involves a little bit of finite field operations, which we'll introduce today. But now let me just finite field. Okay. Let me just give you guys a brief idea. And then when we're done with finite fields, we'll come back. So this it uses something that's similar to AES because this is related to finite fields. So I will give you guys a general idea, and then when we are done with this finite field introduction, then we'll come back. So anyway, this is especially good to use in conjunction with AES encryption. Okay, so the encryption is, we have an initial value, we have a key and then the initial value I, and then we encrypt IV with key, and then we perform this type of thing. This is a finite field raised to the power of something. We'll come back later. Okay? And then it's going to be XORed with a plain text. Okay? And then do AES encryption and so on and so forth. So this is XTX mode. XTS. Okay. We'll just give you guys an overview, and then we'll come back later. Okay. So, because today we'll be talking about the finite field. So that's let's temporarily stop the modes of operation, and we'll come back later. Let's talk a little bit about cryptanalysis. So cryptanalysis is just a way to attack ciphers, block ciphers, any cipher. And it's a huge area, and it's also an area that lots of people are doing research on, because in the community of cryptography, there are tons of hackers. They're trying to crack those ciphers. Among them, there are some most powerful methods are related to statistics. So statistical attacks, the most powerful. There's a one called the first one is called differential cryptanalysis. And these are really deep topics, and it's difficult to analyze. But anyway, I just want to give you guys a simple idea. It's pretty much finding the difference between the previous block and the later block, and then compare them, and then try to find any relationship. If there's any relationship to be exploited, then you can reduce the size of exhaustive key search. From a cryptographic point of view, those attacks, it's not completely compromise your system. Okay, so it's never like that. From a cryptographic point of view, if the let's say if the exhaustive key search, we need to perform all 64-bit exhaustive key search, then it is a lot. But if we can reduce that, let's say we reduce 10 bits, then that means your algorithm has some weakness. Okay, your algorithm is designed to use with 64-bit key, but if you have some internal relationship, so the attackers can exploit, then they can take advantage of those relationships to reduce the number of exhaustive key search. That means your algorithm is not designed perfectly. There's some internal weakness. Okay, in that case, we say this algorithm is not good. Okay, there are many examples like that. For example, even though like hash algorithm, we were going to introduce later, like MD5, designed by Ron Rivest. There's some weakness, so then there's some repeated pattern that can be exploited, and then people can take advantage on this to reduce the number of exhaustive key search. That's it. That's already bad enough. So the cryptographers, they're not really, just compromise. It's almost impossible to completely compromise an algorithm. But if you can reduce the difficulty, then the algorithm is not designed perfectly. The DES was designed perfectly because so far there's no good way to do anything less than 56-bit key search, exhaustive key search. No better than that. Okay, differential cryptanalysis is a chosen plaintext attack. It compares the two blocks of internal steps. We can call one m plus 1. Okay, the other is mi plus 1. The other is mi plus 1 prime. We compare those and try to find a relationship between them. Okay, let's take DES for example, or anything that is a FISO structure. So we have an F. Okay, this is a FISO structure. If we can exploit it, if we can find some relationship between those. So by a relationship, I mean anything related to the plaintext, key, ciphertext. If there's any relationship, one relationship, for any relationship you find, okay, each one will reduce a bit of exhaustive key search. So let's say you have 10 relationships known, then you can reduce the 10 bits of exhaustive key search. That's the idea. Okay. So this is differential cryptanalysis. There's just trying to find input difference, giving some output difference. Okay, and key. Okay, so that the probability, the statistical distribution deviates the uniform distribution. Okay, then that's differential cryptanalysis. There's another one called linear cryptanalysis. It is used. The idea is to use a linear function to simulate the behavior of your encryption algorithm. This is called the linear cryptanalysis. Okay, these are commonly used for some algorithms are not well designed. These modes, these cryptanalysis can make a difference. Okay, so that's this part. Now we're moving on to finite fields because the goal is to introduce the advanced encryption algorithm, AES, and also the XTS algorithm that will make use of the finite fields. So we'll talk a little bit about this. And we will be introducing a pretty easy version. We won't get into any details. But I'm also teaching another course. It's called mathematical methods. In that course, towards the end of the semester, I'll cover more on finite fields, in a more in a deeper way. Okay, more theoretical way. So, so this is finite fields. So the first thing that I want you guys to know is that we have something called modular arithmetic. So this is clock arithmetic. We only have 0 o'clock, 1 o'clock until 11 o'clock. So we only have 12 numbers. But we can think of this as, this type of clock arithmetics, it wraps around. If anything goes more than 12 o'clock, so 12 o'clock, we can subtract 12 and then consider it 0 o'clock. So 1 o'clock is the same as 13 o'clock. That's clock arithmetic. And they follow pretty much the same rules as ordinary integers, ordinary integer arithmetic, except for little things. So we can say, for example, 1 o'clock plus 3 o'clock is equal to 4 o'clock, something like that. And there's only some difference. Okay. So the difference is actually easy. So anything that goes beyond 12 o'clock, we can subtract 12 from that. So in this sense, we can always limit the number to the range of 0 to 11, okay? or 1 to 12, whatever. Yeah. To make it easier, we consider it 0 to 11, and then we can introduce this mathematical operator called mod, a mod n. So a mod n can be well defined. If you use in the language of C or C++ programming language, we have this percentage operator. For example, like 7% 5. What is that? It's actually 7 divided by 5, integer division. So you get the remainder 2. So this is equal to 2. So this is mod. This is kind of like a mod. So you have a number that's divided by another number, integer, and then you get the remainder. But this can be done in the sense of modular arithmetic. And in math, we use like 3 bars. But sometimes it's difficult to type a symbol, so I sometimes use 2 bars. But we do have a special name for that. In math, this is called conjugacy. Okay. And also, if, for example, like this reads A is congruent to B. Congruent. A is congruent to B. There's a Chinese word for that. It's called 同语. Mathematicians like to use this symbol. Okay. Yeah, congruency. I'm sorry, not conjugacy. Congruency. So A is congruent to B. It reads this way. Okay. In Chinese, we say A 同于 B. So they actually means A and B have the same remainder. Let's take a look at the module 7 example. So we can group those together. So we have 0, okay? So 0 is regarded as the same number as 7 if it's modulo 7. So these two integers are regarded the same. 1 is regarded as the same to 8, so on and so forth. And then you can go backwards to negative numbers too. So that's congruency. Module 7 example. So we can define a modular operator, A mod n. The A mod n is defined as the remainder when A is divided by n. Okay? And then we say A is congruent to B modulo n. Okay, so we use this way too. Some mathematicians call B. Okay, the rest. So for modular arithmetic operations, if you slightly relax this a little bit, then we end up with a different set of arithmetic rules, which look kind of similar to what we have learned in school, in primary school. So you guys will feel that it's very similar, but something is a little different. So for example, I mean, according to these rules, we do have we do have this relationship. So you do a plus b. This is ordinary integer addition. Okay. You do addition, integer addition, and then after the addition is completed, we do mod. It's going to be the same as you do mod first. Okay, and then you do addition, and then you do mod again. That's the same. So for addition, this is no big surprise. But what's interesting is that even for multiplication, it's the same. Okay. So you have two numbers. You do integer multiplication first. After it is completed, you do mod. It's going to be the same as you do mod first, and then you do integer multiplication, and then you do mod again. So we have a mod 5 example. So we can list the addition table and multiplication table according to this way. It's very similar, but something is a little different. So maybe that will be, I mean, for example, like 3 times 3 is equal to 4. This is a little weird, right? But anyway, it makes sense. It makes sense in the sense of congruency. Here, 4 times 4 is 1. Yeah, that's a little different. So some things are similar, some things are different. This is the arithmetic, modular arithmetic. And divisors, okay? A number divides A, okay? If, let's say B divides A, if A is a multiple of B, okay? So B is called a divisor. In this case, this divisor in English, okay? It is translated into Chinese as different technical terms according, in different situations. Here we call 因数. So it's actually the same as a factor. So these two are synonyms in this sense, factor. So B is a factor of A. Okay. And then we denote this by B and then vertical bar. B vertical bar A. It reads B divides A. So B divides A, okay? B divides A. B is called a divisor of A, okay? So that's divisor. Sometimes in English, well, actually, in English and Chinese, they are pretty similar in this case. See, we say B divides A, right? B divides A. In Chinese, we say 整除 B 整除 A. Okay. B 整除 A 是 A 拿 A 除以 B 哦。好 ，B 除 A 是 A 除以 B 哈，这要注意一下哈。So B divides A. A is divided by B. A is divided by B. A is divided by B. A 叫除以 B. 所以 A 除以 B，A 是被除数 ，B 是除数。那除数会去整除 A， 这是对的，这刚好中文跟英文是对的。除叫做 divide， 除以叫做 is divided by， 所以除以刚好是被动，所以要注意一下。好，那我们讲整除是主动啊，不是被动，所以是因数要整除一个大一点的数。这刚好中文、英文是一样的，对，对。事实上，这些东西是从那个，这些东西是从应该是清朝那时候过来的。清朝还有头先整理，我有同学看过 YouTube， 就有个数学老师，他发现有一份清朝的微积分课本，你知道吗？他没有看过吗？我等下给他看，里面有很多中文字，这很怪，对，很妙。Anyway, so just to make sure that we're using the same language. So B divides A. B divides A. Okay, A is divided by B. So for modular arithmetic, we can consider this. Okay. Now we can call for modular arithmetic of 12. We already know that. In such a world, we have pretty much the same thing as addition, subtraction, and multiplication. So three arithmetic operations, we can do pretty much the same thing. It's just a little weird. Sometimes when you handle multiplication, it's a little weird because it wraps around. A little weird. But other than that, it's similar. Okay, especially addition and subtraction, they're similar. If we generalize this idea to modulo n, then we can consider the zn. This z, usually we write z in this way. The zn is usually it's usually written in this way, with double strokes like this. Okay, but I can't find any symbol like that in PowerPoint. So then I use this. Okay, so the Zn. Zn is defined as the set of integers from 0 to n. 0 to n minus 1. And then we consider three operations: addition, subtraction, and multiplication. Okay. So we have addition and subtraction. These two are coupled because subtraction is the inverse operation of addition. And then we have an extra multiplication. And mathematically, we say this forms a commutative ring. And we'll explain this later, what this means. Commutative ring. And then if we do that, then we can realize that it follows pretty much the same rule as our ordinary arithmetic operations. For example, we can have this cancellation law. This is if A plus B is congruent to A plus C mod n, then what we can do is we can almost cancel this. It follows very similar rules of ordinary arithmetic. So A plus B is congruent to A plus C mod n. So when we are in elementary school or maybe junior high school, when we see this, we really can't help doing this, right? We can cancel this A. This is called the cancellation law. Cancellation law can be applied here. It can be applied here. Cancellation law. It makes sense. Yeah. But this, for multiplication, it follows a different rule. Okay, sometimes you can do this, but sometimes you can't. Okay, for multiplication, I mean, in our ordinary arithmetic, integer arithmetic, if A is 0, then we can do the division because nobody can divide by 0. But in this case, it's not just 0. Sometimes you have weird things. For example, mod 6. Okay? Mod 6, for example. So 2 times 3 mod 2 times 0, right? Mod 6. So this makes sense because 2 times 3 mod 6 is 0, and this is also 0. Apparently you can't do this. Because if you do this cancellation law, 3 is going to be congruent to 0, which is false. This is incorrect. But 2 is not 0. So even though 2 is a non-zero element, you still cannot do cancellation law. Sometimes you can, sometimes you can't. We have some relation. This can be done only if A is relatively prime to n. So in this case, if we want to cancel 2. So 2 is not relatively prime with 6 because their GCD, the greatest common divisor, is equal to 2. So if there's any factor other than 1, then this is not allowed. I will elaborate more on this later. Okay, let's talk about the greatest common divisor. In high school, when I learned in high school, junior high school, my teacher taught me this is called the highest common factor, HCF. So I'm sure that maybe you guys, some of you have learned this technical term. But anyway, HCF is commonly used in high school for in math courses. But in programming courses, we call it greatest common divisor. They are synonyms because the highest is the greatest factor is the divisor, so they're the same thing. So an HCF is a GCD. Anyway, we use GCD because this course is more like a programming course. It's an elementary concept in number theory. This is the greatest common divisor. So the greatest common divisor can make sense if you have the concept of divisor. So divisor we just learned what's a divisor like this. 24's divisors are 1, 2, 3, 4, 6, 8. Okay, 12, 24. So these are divisors. 因数, the factors of 24. So for two integers, the greatest common divisor is, there may be, so for two integers, if there is an integer that divides both A and B, then it is called a common divisor. It's called a common divisor. There may be many common divisors. Among them, the largest one is called the greatest common divisor. Okay? So we have an example. 60 and 24, the common divisor is 12. Okay? If two numbers, their greatest common divisor is equal to 1, then this is called the relatively prime. They are called the relatively prime. There's a 互值. Relatively prime. Okay, so these concepts are very similar to the math we learned in high school. And we have an algorithm called Euclid's algorithm. 中文叫辗转相处. Greatest common divisor is when I learned in high school. In our let's use the example 60 and 24. My teacher taught me how can we do? How can we find the greatest common divisor? For example, like 60 and then 24. I'm sure maybe you guys learned similar things as I did. So first, my junior high school math teacher taught me we use test division. So let's see whether 2 divides these two numbers, and then we test 3, and it's 4, so on and so forth. That's it. Let's see 2. So we do test division. So this is what? This is 60 divided by 2, and then we find out 2 does divide 60. Yeah, because the 2 times 30 is 60. And then this is 12, right? Have you guys learned similar things like this? Yeah. And then we do test division again. Let's see. Can we divide by 2? Yes, 2. And then we got 15. Okay, and then we have 6, right? And then we repeat this process. In this case, we cannot use 2 anymore because 2 does not divide 15. So let's try 3. Okay. So 3. Okay, we can do division. Okay. So anyway, here we have to stop because we can't go any further. Okay, because they are we have 5 and 2, and then they're relatively prime. And then this is the greatest common divisor, which is 2 times 2 times 3, which is 4. That's why I learned in junior high school. But this is not efficient. It's not a good algorithm because, number one, it doesn't guarantee that it's not guaranteed that you will always end up with an answer. Okay? So if you're extremely unlucky, then you have to try. I mean, you have to try all different factors, which is very inefficient, right? And there is a better way to calculate this. It's called the Euclid's algorithm. 这个辗转相处。辗转相处呢，可能同学们也学过不同的版本。So I guess maybe you guys learned different versions. Let me show you what Euclid's algorithm is called. So this is called Euclid's algorithm, sometimes called the Euclidean algorithm. Google says it's Euclidean algorithm, but in most math books we say Euclid's algorithm. Anyway, it's an algorithm developed by Euclid, the Greek, some 2,000 years ago. Okay. What I learned is something like this. Have you guys learned this? 60, 24. 我不知道大家有没有学过像我这个版本 Maybe you guys did. First, we take a look at this, okay? And then we divide the bigger one by the smaller one. Okay, for example, like, so this is bigger, this is smaller. And then we try, okay? For example, like, this should be 2. 就60先除以20那就是2倍，3倍会超过。So the result is 2 because if we multiply 3 by 24, it's going to exceed number 60. So then we have 48, right? And then we subtract 60. We subtract 60 by 48, we get 12. And then we divide this by this. We divide this by this. And then we find this is 2. Okay? And then we're done. So this is called the greatest common divisor. This is called the Euclid's algorithm. 这个叫转转相处。这个叫转转相处。Let's take a break. So this is what I learned in elementary school or junior high school. This is called the Euclid's algorithm. And this is done by hand calculation. If you write a program to do that, it's going to be very different because computer does it in a different way. So if you use, for example, any programming language, any procedural oriented programming language, it's going to be like this. It's very, very short. Just use a while loop. Anything similar to a while loop can be done. So this is Euclid's algorithm. It's a classical algorithm. And let's take a look at another example. So let's find the GCD of 1970 and 1066. Well, you can definitely write it this way. This is the way that I. Okay, 1970, 1066. Okay. Yeah. First, we divide 1970 by 1066. So this is the 1970 is equal to 1 times 1066. 1 times 1066. Yeah. The remainder is 904. 904. Okay. And then now, Euclid's algorithm tells us that we have a new division. So we divide this, okay, 1966 by 906. So the remainder becomes the divisor in the second iteration. The second iteration is also this 906. This is 1 times 906. This is the 162. Okay, and then we do it again. This is 5. Okay? Then so 2 times let me see. Perhaps 870. Okay? This is 96. So keep doing. Okay. The result is 68. Keep doing. Okay. Okay, so finally we stop. So this is what I learned in high school. But actually, now, we actually prefer this type of calculation instead of this way, because it's going to be easier for us to do the backward substitution in order to find the multiplicative inverse. I'll introduce later. So this is only part of the algorithm. It's finding the GCD. Okay? This algorithm can be extended to find the multiplicative inverse. Now we will explain later. The multiplicative inverse plays a huge role in the area of arithmetic. And we'll talk about this later. Now, so these are kind of like preliminaries. Now let's come back to the main topic, finite fields, because this is what we're going to learn. This is a really important concept in cryptography because it's used extensively in lots of algorithms, including the AES, the elliptic curve, the IDEA, which is a block cipher, and also there's another a public key cryptosystem XTR, and many others as well. So it's very important in cryptography and also error correcting code. Okay. The idea of finite fields is that it supports all 4 types of operations: addition, subtraction, multiplication, and division. So all 4 operations. These operations are very similar to the arithmetic operations of we learned in high school: addition, subtraction, multiplication, division. Although these operations are purely abstract, they follow pretty much pretty much 99% of the rules of what we learned. So it's very, this type of topic for me when I first learned it, it's something that is very familiar, and it's something that's both very familiar and not that familiar at the same time. So I would say like 99% they're the same, but there's some of them that are very different, and then the difference is huge. So that's finite field. So in mathematics, these operations, these 4 operations are really important. 4 operations is really important. Sometimes you just need to use all four, because these operations, sometimes they're number one, they can be applied to vector spaces directly, because all vector spaces are defined on a field. So if you have a field, then it's very easy to apply linear algebra tools. It's extremely useful. Well, you guys may say we already have some useful fields. For example, like real numbers, complex numbers, or rational numbers. They are good, and then they tell us the story. It's easy to apply, but there's just one fundamental problem. You can't represent a real number using finite memory. That's the only problem. You can't, okay? Because you have to deal with infinite irrational numbers. Okay, so the number of digits after the decimal point is unlimited, and then they may or may not have any patterns at all. If they don't have any pattern, for example, like pi 3.1416, it's going on forever, and then you don't know what the next digit is, right? That's a problem. So it's impossible to use finite memory to represent those. Well, sometimes you just need all four operations, but the problem is you can't use finite memory. Or sometimes you can use approximate numbers. You can just truncate these numbers, so that you only go up to some digit after decimal point. If you can sacrifice a little bit of accuracy, then it is fine. So in many cases, in lots of areas of engineering, if you can sacrifice the accuracy, then it is okay. But in many operations like cryptography, you can't sacrifice anything, because if you sacrifice a little, even just a tiny little bit of accuracy, you can't decrypt, because everything is just gibberish. So in that case, if you need all four operations, what do? You have to sacrifice others as well. So mathematicians found that, okay, in these applications, cryptography and error correcting code, there's no way you can sacrifice accuracy. So if you want to make these systems work, we have to sacrifice others. So what's the others? That's the intuition. So sometimes you sacrifice intuition a little bit and make those operations a little more abstract, but the system can still work. That's the idea of finite field. So in order to introduce the full concept of finite fields, we have to introduce groups first. So first groups, then rings, then fields. Because for fields we need 4 operations. For rings we need 3 operations. For groups 2 operations. 好，重点是4则运算，一定要4则。我们必须要用到4则运算，所以这种结构叫做 field， 就是中文叫题哈 field。但这个字哈 field 这个字数学跟物理不一样，物理的 field 叫做场，这两个没有关系的。物理有什么量子场论，那个场 quantum field 跟这一点关系都没有。数学的 field 叫体，体育的体。那这4则运算，我们要定义4则运算，你要先搞清楚什么叫3则运算，所以我们要先讲叫 ring。但是你要先讲3则运算，你还要比它更基本叫2则运算，叫做 group。就要先讲 group， 再讲 ring 和 field。但是历史上的发展刚好是倒过来，它概念是先有 field， 再有 ring， 再有 group。group 其实是最晚才定义的。但是最晚才定义，但是我们介绍的顺序，以所有的书，没有任何一本书是先讲 field 再讲 ring， 没有这种东西。因为 field 的定义，你用先讲 group 会更好讲，顺向的思考是比较容易。但是数学家一开始 ，so actually mathematicians when they first conceptualize the idea of fields, They don't know what the conditions they need, right? You need to have some conditions or properties, mathematical properties. But the mathematics is like that. You can think of it as a black box. You have some properties, right? You have some definitions. And then if those definitions are satisfied, then you end up with some results. That's math, right? But the ideas math is that, okay, the topic we talk about should satisfy some assumptions, right? So you have some assumptions first. Assumptions. Okay, first you have some assumptions, and then after the mathematical deduction, after we do some mathematical deductions, we end up with some results. Okay, deductions. These assumptions shouldn't be too strict, because if the assumptions are too strict, well, then you can have really beautiful deductions and you get very good results. But because your assumptions are too strict, the applicability of your result is very limited. It's just extremely limited. So for example, like when you have an assumption, you can have assumption like, okay, the students in this class whose height is less than 170 centimeters. Now, this is an assumption. But this assumption is very strict. So anybody who is shorter than 170 centimeters, you have very limited people, right? But let's say if you have another assumption, the height, any student in this classroom whose height is less than 200 centimeters, then this assumption almost have no effect at all, because nobody is that tall. So that assumption is very loose. So your assumptions can be very strict and also very loose. If your assumption is too strict, like I said, okay. For example, let me deduct a rule. Okay, I just randomly say something. So for any students in this classroom whose height is less than 150 centimeters must be a female. Okay, something like that. It won't make any sense because nobody is shorter than 150 centimeters, right? That's too strict. Well, you have some results, but that result is useless. Okay? And well, you can say, okay, the student, any student in this classroom whose height is less than 200 centimeters must have 2 eyes. It is useless. It's useless too. I mean, this assumption is very loose, but the result is very trivial. Okay, it's true. Yeah, it's true, but the result is useless. So for mathematicians, the important is you have to balance the assumptions. It shouldn't be too loose. It shouldn't be too strict either. You have to, balance these two so that your assumptions are appropriate, not too loose, not too strict, and then you get useful results. That's the beauty of mathematics. Okay. Otherwise, it's useless. So in order to do that, initially the mathematicians, they don't know what assumptions are loose, what assumptions are strict. After a few hundred years, they start to realize, because of the development of mathematics, they kind of know that what assumptions we really, really need. So after a few hundred years of development, they finally came up with the idea of groups. That's why when we introduce the concept of groups, we do it in the reverse order. That may be a little counterintuitive, because when we start to learn, we don't know why we need these rules. But the thing is, if you start with those rules, everything will be smooth. That's the idea. So that's why the mathematicians they developed this way. Let's talk about groups. So after a few hundred years of development, they end up with five assumptions, and then those five assumptions are absolutely critical. And then the order of assumptions is also important. The more on the top means it's more fundamental. Okay, so it's kind of like a list of requirements. Whatever is on the top is more important. 好，这就是100年来发现最重要的5条。所以我们一开始看这5条，你可能没有什么感觉，因为你不晓得哪一个重要，哪一个不重要。但是数学家已经经过几百年发展，最后就是这5条最重要。对，你可以少也可以多，那就看你需要什么。那我刚刚讲的数学太严格跟太松不行。太严格的假设，你的结果非常的好，但是没有用，因为符合你这种条件的这种讨论的东西太少了，大家都不符合你的条件啊。对，假设就是我刚刚举个例子啊，在我们教室内，这个身高不到150的，假设我随便乱讲，身高不到150公分的同学一定是女生，假设这样的。这个 rule 可能是对的，但是没有人身高是小于150，所以你这个 rule 也没有用啊，它是对的啊，但是它没有用，是这个意思。所以太松不行，太紧也不行，你要必须不多不少，刚刚好，是这样的意思。这4条 ，so the order of importance is this. Number 1, closure. So they have names: closure, associativity, identity, inverse, and commutativity. They're listed in the order of importance. Number 1, closure. This is the most important. So what is a group? A group is a set of elements. Finite or infinite, doesn't matter. But it's not just these elements. Okay, you have to have some operation defined on that. And that operation can be anything. It can't be just a table. Okay, it's abstract. There's you can use arithmetic operations and their combination to specify this operation. That is fine. Or you can also list a table as long as it satisfies these requirements. Number 1, closure. When you have 2 elements in G, okay, after you do this operation, it should be in G again, so that we can go on. Otherwise, there's nothing to talk about if you have an operation, and then after you do this operation, you have no idea what it is. Then we can't go on because we have the center of our interest. The subject of interest is a group G. Okay, if anything beyond that, then we can't go on. So closure is the most fundamental. Number 2, associativity. Well, you guys may know that there's associativity, there's commutativity, okay? But mathematicians do find associativity is more fundamental than commutativity. Why? So this is associativity, okay? 结合律. Commutativity is you can switch the order. Why this is more important? 为什么结合律比交换律重要呢？结合律是不是比交换律重要？结合律绝对比交换律重要。为什么？其实我们就看一些实际的例子啊，对啊，就是有东西结合律对，交换律不对，有没有同学给个例子给我？很简单的例子，矩阵啊，矩阵乘法，而且你不同维度的结合律是成立的，但交换律不成立。所以显然矩阵按照矩阵这种说，结合律是比较重要，还不止这一点。So matrices, matrix multiplications. Associativity holds, but not commutativity. So this is a concrete example that tells us that associativity is indeed more fundamental than commutativity. And there are many other examples too. And there's more than that. Why this is more important? Because let's say if they are not equal, let's say the associativity does not hold, then what happens is that how to parameterize makes a difference. So you can't omit the parentheses, if associativity doesn't hold. Let's say, we sometimes we write it this way, right? If you write this way, without parentheses, you implicitly assume that associativity holds. Otherwise, this expression will be ambiguous. Right? Because without, let's say if they're not different, if they're not the same, then what do you mean by A times B times C? Do you mean by this? Or the other? Right? We've already taken this for granted. That's why we write it this way. For matrices, for anything. Because so far, what we have learned, associativity always holds. We have never learned anything such that associativity doesn't hold. Right? So that's the idea. 所以结合律我们应该是从以前到现在从来没有学过任何一个结合律不成立的一种数学。你有同学学过吗？你告诉我哪一个东西结合律不成立？其实我可以造出一些人造的例子出来，但是你不会学过，因为结合律不成立，你基本上没有办法再讨论了，这个东西太过重要了，所以结合律不成立根本没办法。Then identity. Identity is a concept that's related to the whole group. So the idea is very simple. So when you do it, you have a special element within this group, such that when you do the operation with this special element, it's the same as not doing any operation at all. It's this. So according to different operations, you may have different identities. For example, for addition, okay, the additive identity is 0 because we have this. Okay. Anything added to 0 won't make any difference. Okay. For multiplication, obviously, it is 1 because you have this. Anything multiplied by 1 is the same thing as not doing any operations at all. So for multiplication, it's this. For addition, it's this. So this is called the multiplicative identity. This is called an additive identity. Okay. It's not just numbers. You can have similar concepts. You can generalize similar concepts to many other things as well. For example, for addition, let's say we talk about a matrix, for example, like n by n matrix. So the additive identity, okay, is this, the all 0 matrix. This plays the role of additive identity because this all 0 matrix, if you add to any matrix of the same dimension, it won't make any difference. Okay. Similar thing for 1. Okay, that's the identity matrix. Okay. If you multiply this identity matrix to any matrix, it's the same. So this is the multiplicative identity. This is the additive identity. Okay. And then whatever it is, we can generalize this to any other mathematical operations. Even though, those operations may not be describable. Maybe you just give me a table or something like that. That is okay. It can be complete abstract. And then we call this identity, additive identity, because it is similar to 0, we use the symbol 0 to represent additive identity. We use the symbol 1 to represent the multiplicative identity. Okay, so from now on, 0 may not be an integer. It's just a symbol. Okay. In whatever mathematical structure you define, the additive identity is 0. We use 0 to represent that because it makes us easier to understand. And also 1 is the multiplicative identity. So that's the identity. And then inverse. to the group, the inverse. But the inverse for addition, okay, for any number, the inverse is very easy to understand as well. So if you have any number, okay, let's say any integer, your inverse for addition, you have any number, for example, like 5, the inverse. If you talk about addition, then its inverse is -5. This is the inverse. If you talk about multiplication, okay, this is your inverse. Okay, so this is the multiplicative inverse. This is the additive inverse. Okay, so you want to have the inverse. So these 4 rules are most fundamental. And then there's a fifth rule. And it's also important, but not as fundamental as the first 4 rules. That's commutativity. If you can commute, then it's more important. It's great. And then you have more property. And this is called a abelian group. It's not called commutative group. Yeah, it's called abelian because this was first proposed by a Swedish mathematician, Henrik Abel. We call it abelian group. He first came up with this idea of commutativity. And then what's funny was the abelian. This word derives from a name, but the first letter is not capitalized. Yeah, there are many adjectives derived from names. Mathematicians, physicists, whatever. Their names, their first letter is always capitalized. For example, like you have Newtonian. I can write a tons of books. Newtonian, right? Newtonian mechanics, Gaussian, right? Newtonian, Gaussian. Okay. Many others, Cartesian, right? Cartesian product. Cartesian, Archimedean, Einsteinian. There are lots of those. Hessian matrix, Hermitian. They're all capitalized. Hermitian. So a ton of those. Lagrangian, Hamiltonian, everything. There's only one exception. Abelian. It's lowercase. This is the only adjective derived from a name, which is not capitalized, in which the first letter is not capitalized. There's no exception. No matter how great you are, you can't have your name written in all lower cases for some mysterious reason. We don't know. It's a mystery in that. I mean, some people say maybe this is just way too important, so that people regard this as an ordinary adjective, so that it's not. The first letter is not capitalized. I don't know. 就是一个数学界的一个谜，为什么它的名字当形容词是小写的呢？到现在为止是个谜。你真的后面再去找任何只要是人名变成形容词的，没有任何一个字，它的第一个字母不是大写的，没有这种东西。所有不管数学家、物理学家、化学家，所有的东西，所有科学上的名词全部都这样，没有任何例外，唯一一个例外 abelian。Okay, so let's take a look at some example. Okay, we have let's say the set is 0, 1, 2, 3. So only 4 elements, and the operation is addition mod 4. Okay, so we add anything, any of those mod 4. Okay, that's the operation. G plus is an abelian group. You guys can check all five assumptions hold. So this is an abelian group. All five assumptions hold. So that's the first example. Let's take a look. G0, 1, 2, 3, and then operator. The operator is multiplication mod 4. Is G with, along with such multiplication, a group? 请问一下，这是 group 吗？ Is this a group? You know, in order to be a group, all 4 operations have to hold. Okay? As long as any operation fails, it's not a group because it violates the requirement. If it's a group, everything has to, be satisfied. As long as anything, if you have one thing that violates the rule, then it's not a group. 好，这是不是 group 呢？这个是 group 吗？那哪一条不成立？哪一条不成立 ？Inverse. 谁没有 inverse? So which element does not have an inverse? Actually, 0 does not have inverse. 2 does not have inverse. 3, how about 3? 3乘以3 mod 是多少？3乘3 mod 是等于1哦，所以3是有 inverse 的。3的 inverse 是自己，1的 inverse 是自己，另外2个没有，所以 inverse 是错的 ，inverse 没有办法被满足，所以它不是 group。So it's not a group. Well, but anyway, we can, let me give a number. So this is the most fundamental. We call this G0 because it's the most fundamental. G0, G1, G2, G3, G4. So the order of importance. It's listed according to the order of importance. G0, G1. So sometimes even if it's not a group, such structure may be useful as well because mathematicians they found that. Okay, these two is a cutoff point. This is the kind of like a sweet spot. Okay, if you cut off here, it's not too loose, not too strict. So it's kind of like a sweet spot. So most people will find it useful here, but it does not mean anything, looser than that or anything stricter than that is useless. Okay. 好，所以这个刚好是个甜蜜点嘛，大部分人会觉得这个是最有用的。但是这不代表说，好，你松一点或你紧一点，这东西没有用，不是哦，只是说那个东西可能没有那么有用，但不代表没有用。所以这个叫 group， 这甜蜜点嘛，对不对？那你说一半呢？一半也有用，数学家也有，一半叫 semi group， 刚好一半，这叫 semi group。那你到这边更好了，这叫 abelian group。abelian group。那到这边也有啊，到这边也有啊，那这边有这边的结构了啊，这边有这边的结构。所以这边有另外的名字哈，这我就不讲了，反正这些它都各有各的用处，也不是。所以同样你如果去数学系看，是有 semi group 的书，专门讲 semi group， 只是一般人比较少用啊，但是不代表它没用啊。那也有 abelian group，group theory 里面有专门讲 abelian group 的，也很有用啊，abelian group 相当的有用。所以这个就是大概是个甜蜜点啊，它是个折中，不是说所有的都要这样子。So anyway。Let's go back. So this is not a group, but it's a semi-group. Yeah, this is a semi-group. Let's look at this. So the element. Let's look at another example. So G is equal to 1, 2, 3, 4, and then the operator is multiplication mod 5. Multiplication mod 5. Is this a group? Yeah. So actually, if you guys look at these examples, what can go wrong? It's usually G3 because inverse is, sometimes you don't have inverse. do we have inverse for every element? So once inverse, well, if we look at the multiplication table, then it's very clear. Okay? So let's do mod 5 operation. Okay? Because we're talking about multiplication. Okay? So it's 1, 2, 3, 4. So 1 times anything is anything. Those things. 2 times 2 is 2乘2 mod 5. So 2 times 2 mod 5 is 4. Okay. 2 times 3. 2 3等于6 6 mod 5 becomes 1. 2 times 4 is 3. Looks a little weird, right? But it's okay. Like 3 times 3 3 3得9 9 mod 5. 所以9 mod 5变成4。9 mod 5 9 mod 5 3 4 12 mod 5变成2。4 4 16 mod 5 4 4是1，就变这样子。So you have an upper triangle, and then you can fill out the rest of them by do this symmetric. And then this is 1, okay. This is 3. And then if we look at the inverse, let's see. For every element, you should find some element so that when they multiply together, it's equal to the identity. So 1's inverse is what? 2's inverse is 3. Okay. 3's inverse is 4. 4's inverse is 3. Okay. Okay, so we do have an inverse. Sorry. 4's inverse is 4. 3's inverse is 2. So in other words, 2 and 3 are inverse of each other. 1 and 4 are inverses of themselves. So everybody does have an inverse. Everybody does have an inverse. So G3 is satisfied. So it's actually a group, not just that, because commutativity also holds. So it's an abelian group. So this is an abelian group. Another example. Let's take a look at 1, 2, 3. This is G, and the operator is mod 5. Is this a group? Yeah, obviously it is not. Okay, 2 and 3 are inverse of each other, so it's okay. 1 is an inverse. That is okay. But G0 fails because 2 times 2, it goes out of the set. So G0 fails. Well, this is surprising because inverse holds, but closure fails. So actually, usually when we check these conditions, it's usually either G3 fails or G0. These two assumptions are most problematic. Usually G1 and G2, they're fine. So this is not a group. Okay. Another example. G is 1, 2, 3, and then operator is mod 4. Is this a group? Is this a group? Mod 4. In this case, let's take a look at 2. Okay, 2 times 2 is equal to 0. It also goes out of bound. So G0 fails. And also, 2 does not have an inverse. Okay, so this fails. In this case, 3 has an inverse, 1 has inverse, but 2 does not have an inverse. So both G0 and G3 fail. So this is not a group. Okay. So that's all about groups. The concept shouldn't be too hard. It's a little abstract, but it shouldn't be too hard. Let's talk about rings. So groups actually have groups have two operations. One is the multiplication. We call multiplication. The other is its inverse. because G3 always hold. So this operator has an inverse operator. Okay? So that is why we say there are two operations. Rings are the ones that have three operations. Okay? Three operations. So that's an addition along with another multiplication. This multiplication can have nothing to do with the addition. These addition and multiplication, those are just symbols. They are purely abstract. They can be anything. They can be anything. So that is why we said this is kind of like a set of three operations. So these two operators are not created equal. Okay, there's one of them that behaves better, is well behaved. The other is a little relaxed. Okay, so mathematicians found that there are a lot of the things we are familiar with. They satisfy these rules. Okay, so actually the template for rings is a set of integers. That's just a set of integers. So if we look at the set of integers. Naturally, we have addition and multiplication. Yeah, we can talk about addition. And then the addition, if we talk about addition alone, it forms an abelian group. But when we talk about multiplication, okay, it forms a semi-group. Because if the inverse may not hold. So this is something that we're really familiar with. Mathematicians didn't come up with this concept out of thin air. No, it actually mimics the set of integers. So the set of integers is a template. So it's an abstraction of a set of integers. So anything that behaves like a set of integers can be regarded as a ring. Okay, so that's integers. So it's a set R of elements in which there are two operations, and R alone, R with the addition alone is an abelian group. Okay, R with multiplication alone is a semi-group. In addition to those, there is distributivity. Then altogether, it's called a ring. Okay. It's called a ring. So that's the concept. The concept is actually very straightforward. So there are two operations. One operation must be better. Okay, better behaved, and we call that operation addition. The mathematicians like to use the symbol addition because when you use addition, we imply that commutativity holds because it's similar to what we have learned. And then for another operation, they prefer to use multiplication because multiplication, sometimes multiplication may not have commutativity. For example, matrix multiplication. That is why they use multiplication. So when they use multiplication to represent something, that something may not have commutativity. 所以数学家比较喜欢用加法去描述一个可以交换的东西。因为我们从小到大所学的任何加法，没有任何一种加法是不能交换的。没有，大家可以仔细想一想。就这个东西符合我们的习惯，所以我们把那种可以交换的用加法表示。但数学家呢，用乘法，我们从小到大学的乘法是很多可以交换，没错，但是就是有矩阵不能交换，对不对？是有一些乘法不能交换，还有别的乘法啊，不止矩阵的，还有一些别的乘法也是不能交换。所以数学家用乘法的话，那也符合我们的习惯，就是你可能有不能交换的情形，那这个时候就这样，有时候可以，有时候不行啊，那我们就不能够放心的说，它可以交换，所以我们就用乘法来表示。那这加法乘法完全是抽象的，没有讲说它是哪一种东西，你可以直接列表规定谁加谁等于谁，就是你一个加法就是一张表，一个乘法就是一张表，里面随便你规定，但是你不能乱规定，你必须符合那些条件，加法必须符合 G0 到 G5，因为它 abelian group。乘法要 semi group 这样。 这种抽象化的结果就叫做 ring。Okay. So so if the ring, so that's a ring. And sometimes you have more than that. When we talk, when we look at the multiplication, we know that multiplication is a semi-group. Okay. So for multiplication, its G2 and G3 may not hold. If G2 holds, then it is called a ring with 1. Because if G2 holds, that means the multiplicative identity exists. If that exists, we call that 1. Because 1 is, it satisfies what we have learned. It's our habit. It satisfies. It doesn't it's not contradictory to anything. So we call this 1. Okay, it's a ring with 1. In addition, if G4 holds, okay, it's called a commutative ring. Yeah, it's just a technical term. They don't use abelian ring. No. If there's a abelian group, there's commutative ring. An example: 0, 1, 2, 3. Okay, along with 2 operations: addition, multiplication, mod 4. Is this a ring? Is this a ring? 0, 1, 2, 3. So mod 4, okay, it's actually a, so you guys can check, is this a ring? 这个是吗？是不是 ring？ 0 1 2 3加成 mod 4，这样是不是 ring？ 符不符合？ So it is a ring. Not only that, is it a commutative ring? Yes. Do we have 1? Yeah. So it's a commutative ring with 1. It's exactly like the set of integers. The set of integers is a commutative ring with 1. Let's take a look at another. Z6. So I have 0, 1, 2, 3, 4, 5. Okay. Mod 6 addition, mod 6 multiplication. It is a commutative ring with 1. We have additive identity 0, multiplicative identity 1. So it's a commutative ring with 1. So additive inverse, no problem. Multiplicative inverse, only 1 and 5 have multiplicative inverse. 3 has no multiplicative inverse. So the elements of a ring may not have multiplicative inverse. This behaves exactly like the set of integers. So you have 3 operations. That's why I said there are 3 operations, because division may fail. Actually, division is the most difficult one to fit in, because in some cases you always contradict with something. So division is difficult. That's the most problematic. 所以除法常常没有，因为整数没有除法嘛，对不对？所以你有时候不能除，你就没办法，这个除法的概念就不存在了。这就为什么会有3者运算，就是因为我们有整数。所以我们人类从以前开始就是先有整数的。那你后来除法，你发现不能除怎么办呢？干脆我们去创造一个东西让它可以除，所以才有几分之几的概念。那几分之几的概念其实是把一个不能除的东西，你把它变成可以除，就把它变成是 field。这就是为什么有理数是这样产生的。这东西在古埃及就已经有了，所以古埃及就会去量那个长度，就会知道几分之几几分之几。这个概念就是把原本不能除的东西让它可以除，把它稍微扩展一点。好，我们今天上到这边，so let's stop here.